Okay, this is the second portion of the course, part 2, hardware. So we're going to start the hardware portion of the course in this lecture, lecture number 9, to cover the 9th week. Okay. First chapter in this portion is the hardware specifications, the specs of the 8086, 8088 Intel processors. By the end of this chapter, we should know the pin configuration of both 8086 and 8088, the clock generation to operate these two processors, how to buffer and latch the buses, and the timing diagram through which these two processors work and operate, and finally the necessity of a wait state in the operation of the 8086, 8088, and we'll know as well the two different modes of operation, the maximum mode of operation and the minimum mode of operation. Okay, here are the pin configuration of the two processors. A is for the 8086, B is for the 8088. And we'll see now, each processor is packaged in such a way 20 of its pins is lined up on the left hand side and the other 20 is lined up on the right hand side. So we have 40 pins, 20 of them lined up to the left hand side and the other 20 pins are lined up to the right hand side. This is why this type of package is called a dual inline package. So pins are dual, they are separated into two groups, two equal groups. Each group is lined up through one side of the chip. This is why we call them dual inline package. Okay, and if you look closely to these two pin configuration, you would find three main differences between the 8086 and the 8088. We know that the 8086 data bus is composed of 16 bits. This is why we have here AD0 through AD15, which means that we have 16 pins multiplexed between address and data. So AD0 through AD15 are 16 pins that can be used to specify an address or 16 bits of data on the data bus. And this kind of multiplexing is very useful because it decreases the number of pins required for each microprocessor, because we have now used 16 pins to cover two different functions, 16 bits for the address and 16 bits for the data. Otherwise you would have to include 32 bits if you are to separate the address from the data. If you are to make dedicated pins for the address and dedicated pins for the data, you would have used 32 different pins, but by multiplexing you only use 16 bits. You can use them for the address and for the data. Once a data is placed, you have to have some kind of indication to indicate whether these 16 bits carries an address or carry a data. Okay, and then the rest of your address pins, 16 to 19, are placed in pin 38 to pin 35, from 35 to 38. and they are again multiplexed with some status pins. If you go to the 8088, you would find only 8 bits are multiplexed between address and data from AD0 to AD7, because the data bus of the 8088 processor is composed of 8 bits. So we need to only multiplex 8 pins, AD0 through AD7. So this is a difference between, or one difference between 8086 and 8088. A second difference is seen from pin number 34. Pin number 34 in the 8086 processor refers to BHE, bus high enabled, and status number 7, S7. If you go to 8088, you will find that this pin number 34, refers to the SS0. And one third difference between 8086 and 8088. In 8086, pin 28 refers to memory or I/O, high for a memory and low for I/O, while the same pin in the 8088 processor does the opposite, low for I/O and high for memory. So these are three main differences in the pin configuration between 8086 and 8088. Okay, so the pin out. Again, the type of packaging of the two chips is the dual inline package. 40 pins divided into two equal groups and lined up in duality, lined up in two lines, one to the left and one to the right. This is why we call it dual inline package. And the differences between the two processors, as we said, AD0 through AD15 in 8086, while AD0 through AD7 in 8088. Pin number 34 refers to SSO bar in 8088, while it refers to BHE bar slash S7 in 8086. And the pin number 28 M slash IO bar for 8086 and IO slash M bar for the 8088. Good. To operate each of these two chips, these are the requirements for the power supply. We have to supply a power supply of DC 5 volt, and we allow only 10% plus minus 10% variation in this power supply for our processor to operate correctly and perfectly. And they draw around 350 milliamps, 360 for the 8086, a little higher than the 8088, which requires 340 milliamps. And they operate in a temperature range 32 degrees Fahrenheit to 180 Fahrenheit. And we can modify a bit this temperature range by using the CMOS technology. CMOS technology, when you use it, it goes down with the power and up with the temperature. And we refer to the 8086 by 80C. 86C refers to the technology used to fabricate this processor is the CMOS technology. In doing so, the power, the current drawn by each processor goes down to the 10 milliamps, and the temperature range varies from minus 40 degrees Fahrenheit to 225 degrees Fahrenheit. Now, a little bit more about the DC characteristics. Okay. the DC characteristic should be known of the processor for being able, for enabling us to interface different components. So when we need to interface components to the microprocessors, we should know the DC characteristic of both the microprocessor and the interface components. So the zero drawn from the microprocessor, the voltage refers to the zero, should be read correctly by the interface and vice versa. So zeros and ones are sent from the processor to the interface components or vice versa correctly. This is why we need to know the DC characteristic. So if we are inputting some voltage to the processors, what is the range of zeros and ones? If we are getting bits out of the processor, what is the ranges of zeros and ones? And here you are. For inputting bits to the processor can sense the 0 for a maximum volt of 0.8 volt and a maximum current 10 microampere. For the 1, this is a minimum voltage that can be sensed as 2 volt, which draws 10 microampere. And here are the levels for the 0 and 1 when the microprocessor outputs the bits or the signal. For example, the standard logic gates sense a 0 up to 0.4 volt, while your processor can go to 0.45 volt. So when the processor sends a zero to this logic, it sends a little higher voltage, which makes your connection overloaded. So this results in a more loads on your connection. So we have to pay attention to the DC characteristics, and both your processor and the component to be interfaced with should be compatible in voltage levels and currents. Good. Here again is your 8086 microprocessors, where the red color indicates the pins that can bring in data to your processor or send out data. Okay, so your multiplexed address and data can send out data if it sends an address, or bring in data if it brings in a data. Good. While pins colored blue, current blue, so these blue pins send out data only. Okay, so they send out data. These blue pins send out data. The direction is going outside, while the green pins bring in data. So this is the pin configuration in a little more details. So the pins of your 8086 processor are divided into 3 groups. A group whose communication is bilateral, in and out. A group whose communication is in only. A group whose communication is out only. Okay. So what are the different functions of your pins? So we're going to go over the different pins of your processor, specifying the function of each pin. For example, VCC, this pin is to be connected to a power supply whose voltage is 5 volt plus or minus 10%. Ground, we have 2 grounds, up ground and down ground. This is the ground pin. This is the clock. So you provide a clock externally or internally through this pin. AD0, as we said, to AD15 are used for address or data. If you are using them, the data placed in these 16 bits are referring to an address. There is a pin called address latch enable, ALE, that should be high. So if a data is placed in these pins and your ALE is high, it means the data represents an address. If AL is 0, it means the data represents a data to be placed in a memory or taken from a memory. It's not an address anymore. Okay. This is E16, the address pin number 16, multiplexed with S3, and it is the same for A17, A18, A19. So this is the rest of your address pins, because your address pins is composed of, your address bus is composed of 20 bits. So you need 20 pins to send out an address. These 20 pins are AD0 through AD15, AD0 through AD15, these are 16, and then A16 through A19, this is the other 4. Okay, S6 is always 0, S5, this is the status number 5, indicates the condition of your interrupt flag bit, if it's high or low. While S status number 4 and status number 3 refers to the segment being used of your processor, meaning if S4 is 0 and S3 is 0, it means you are accessing, you are communicating with your extra memory segment. You're communicating with the stack memory segment, with the code memory segments, or with the data memory segment. Okay. A pin, if it's low, it means your processor is reading. If it's slow, it means your processor is writing. ALE, as we previously mentioned, address latch enabled. If it's high, it means the data represents an address. If it is low, it means the data is a data to go or to come, or to come from a memory or an IO device. Here, data is being transmitted if this is high, or data is being received if this R is low. Okay, it means your data, if it's low, the data is enabled, the data bus is enabled, and data is now available in your data test. If it's a logic 0, your program goes the normal way. If it's high, it means your processor have to wait for a while because it's being communicating with a lower device, a lower speed device. Ready? If it's high, you go ahead and execute your instructions. Otherwise, you will have to wait. Non-maskable interrupt. If this is high, it means there is an interrupt service routine is to be handled immediately. So you don't have to reject it, you cannot reject it, or have it wait for a while. Once you finish your current instruction, you have to go to interrupt number 2, which manages the non-maskable interrupt. Okay, so once this NMI pin goes high, this interrupt service routine will be immediately called after the current instruction is finished. Okay, you're handling now hardware interrupt, so your interrupt should go high. Your interrupt flag bit is also high, and the interrupt is being served, and this is indicated by the interrupt acknowledge when it's low. If this pin is high, it means your processor is in its minimum mode. If it's low, it means it is operating in its maximum mode. Again, high indicates memory, low indicates I/O device. Reset, if this pin is set high for 4 clock cycles, a reset routine will be executed whose starting address is at this address. Okay, hold, if you are to let other coprocessor access your memory, direct memory access, you set this to high. Okay, and this indicates that a hold mode is acknowledged. The processor gives the control of the memory to some other coprocessor. In working in the maximum mode, which means your main processor turns over the control of the memory to some other external processor, you will need to request and grant memory access. So the external processor would always be requesting to access a memory locations in your system and should be granted this access. If you need to set aside some of your peripherals to lock it, to stop this device from being active or communicating with your processor, you have to prefix the instruction dealing with this device by this phrase lock. QS1 and QS0 indicates what's going inside your processor. For example, if they are both 0, they indicates no operation is taking place inside your processor. 0, 1, it indicates the first byte of your opcode is being dealt with, and so on. 1, 0, it empties the queue. 1, 1 indicates the subsequent byte from queue. Okay, we have 3 status bits, S0 through S2. They indicate the function of your current bus cycle. For example, if they are all 3 zeros, this meaning, okay, this means an interrupt is acknowledged. If 001, IO read, IO write, and so on. So these 3 bits are used to indicate the status of your bus. Clock generator. We have a clock generator, integrated circuits 8284A. It generates the clock. No way that your processor can do anything without a clock. It's an ancillary component, a supporting component, an important component to be used along with your processor 8086 or 8088. And it provides some functions to your processor. Generate the clock your processor requires to manage the sequence of events to be taken by your processor. And when resetting your processor, it synchronizes the resetting with the other instructions. If your processor needs to wait for a while, again it synchronizes your processor with the low speed device connected with, and it gives you the levels suitable for some TTL components hooked to your processor. And here it the integrated circuits 82, 84 for clock generation and the different pins, and we'll talk about this in our next lecture, lecture number 10. Hope that everything is clear, and inshallah we'll come back soon after this epidemic situation goes away. Thank you.